Alright, hell yeah. So this might be like part one of a series of, what I want to do is figure out, how the space elevator works, and it should be fairly simple, um, but it's just not super intuitive to me. Like with the space elevator, I have questions of like, well, if here's Earth and here's your hella space elevator, like my first question is, why doesn't it tear itself apart? You know what I mean? Because we have the smokestack analogy that if we're taking down a smokestack and then it starts to, like rotate, and fall. Let's say it cracks and then you got some sort of omega. Well, you generate huge amounts of shear forces to hold itself up. So I just imagine with the space elevator that's not happening, where this thing will actually just kind of break in the middle. Okay, so that's going to be kind of like where I want to go, but this video is like, in physics, you want to just be able to ask a question, and sometimes just one question's enough. And so we're going to be like, well, how high, like off the Earth, do I need to be weightless? And you might be thinking it's just like, well, you can't escape gravity. You know what I mean? So you could be on the other side of the galaxy, and the Earth still exists, you still exist, you have mass, and based on the force of gravity being an equation of gravitational constant, mass of you, and then mass of the Earth, and then great, there's going to be some sort of radius between you and the Earth square. This always exists. So what are we talking about when something can be weightless? And the fictitious force is centrifugal. And I'll even spell this one out because it's how we separate blood. You know what I mean? Like when we throw, if we have something hella spinning, and then we throw in vials, like all the heavy goes to the outside. You know what I mean? So and then so keep that in mind, because on the Earth, we're gonna do a top-down view of the Earth. This is North Pole, South Pole's kind of on the other side. Top-down view. I forget which way it spins. Who cares? I'm just probably going to guess wrong. I don't want to spend the time figuring out what direction the Earth spins. I usually use like New York. Be like, okay, if New York is in the east, oh, for the love, I'm going to do it. So so here's the Earth, north, and here's the globe, and here's south. I live in Montana, and I know to my right is New York. The sun, let's say, is behind the Earth. I can't see it. It's dark for us and New York. But now the sun appears to be rotating in the sky this way. Nah, we are rotating that way because Statue of Liberty gets to see the sun first. I guess Statue of Liberty or whatever. And then we get to. You know what I mean? So there you go. But that's not the point of today's assignment. Today's assignment is just like, can you just ask one question? And so we're not going to try to do any more of those. But I was just like, holy Toledo. If I do a top-down view of the Earth now, the Earth is spinning this way. So weird. I mean, I don't think anyone says that quite a bit. Like, oh, the Earth spins to the east or something. The Earth from a top-down, it spins counterclockwise. Very fascinating. Okay, so yeah, see, that seemed just like a huge waste of time. So now we're going to put ourselves on the equator, and guess what? Centrifuge. We're going to weigh less. So if you want to weigh less, go to the equator. Live there. You only weigh about 8 ounces less. You know what I mean? Depending on what your weight is, and we'll see that in a minute. So now you're like, whoa, why would I weigh less at the equator where you're getting flung off? You know, it's the merry-go-round. So we'll draw another picture. You know, we all have the classic merry-go-round with the little handles, and then hey, you know what I mean? If you're in the middle, shoot, you can get this thing whipping. But if you're just on the very outside and this thing gets whipping, oh heck no, you're gonna be hanging on for dear life, because centrifuge, right? Centrifugal forces. But we don't. We also want to learn about centripetal, whatever. But not too much, because we just want to answer the question of like, well, how high do I need to be weightless? Now we have to structure the problem that actually makes sense. And visually, this should make sense to you. So we know that if the Earth is spinning this way, let's say I built something real tall, you know what I mean, and then got to the top of it, aren't I farther away? Or check this out. So now, you know, you turn this into like Saturn's rings or something. We still have the Earth, but now you built like something really tall that's like a disc that goes all the way around the Earth, and then you take the elevator to the top of that, get a cool view of the Earth, but holy Toledo, you're spinning. You know what I mean? The omega is still the same. That's why we use this term that's in radians per second, because the spin of the Earth down here in radians per second is the same. And it's the same thing as saying degrees per second. You know what I mean? And if you watch the Flat Earth videos, they talk about 15 degrees every... oh, bummer. I kind of forget. Let's see. But we can do it, because there's 360 degrees in a circle. 360 divided by 15. Heck yeah, that's 15 degrees per hour. So there you go. So the spin of the Earth is, we try to do it in degrees. So it doesn't matter if you're in a cave way deep down into the Earth, you're still spinning with that same omega. But our cool equation that we use, or that I like to say, is that radians, no one knows what radians are. So I like to say that radians times radius is something normal. And we'll go over this. We'll go over this. So if this is my radius of my circle, if I make a string and then drape it around the circle, I get to about there. Does that make sense? If I cut a string to the radius of the circle, I can drape it around the circle, get to there. That's 1 radian. And you would have to cut like about 6 radiuses for that full circle. It's actually 6.28. That's 2 pi. All right, but this is the definition of what 1 radian is. And then so we have this term, angular velocity, is going to be in radians per second. That means I traveled that distance in 1 second. Okay, so and then we keep going that speed. So it is like it is constant speed, and as long as we're going around a circle, well, now we can kind of figure out what's our tangential velocity. If we're just going that speed around a circle, you know, we can figure that out. Okay, and so that brings up the question. Oh, yeah, and the first one, what did I say about this arc length? So we said rate. So also 1 radian times radius. This is my axiom. Radians times radius is something normal, and in this case it's the arc length. And it's usually this S term. So radians times radius is the arc length. And then we have radians per second, that's our angular velocity, times radius. Well, that gives us something normal, and that's going to be the tangential velocity. So if we know our angular speed in radians per second, we just multiply by the radius, and we can get our tangential velocity. Okay, heck yeah. Why do we want to know that? Alright, hell yeah. So I guess we don't even need to know that. You know what I mean? Kinda, not really, maybe. But we do need to know, this is where you break out your equation. You know what I mean? So part of acceleration in the normal direction is this term like negative r omega squared. Yeah, I think that's what it is. And we could prove it. Let's say I just didn't know. I wasn't 100% confident of what this acceleration, and I don't even know what acceleration is. You know what I mean? Let's say that. So now we get into learning about radial, you know what I mean, circles. And so if I'm at if I'm at some sort of radius from a circle, there's a few directions I can move. I can just move radially, and we say that's kind of moving in a straight line. I can move around the circle at a constant speed, at a radians per second, and if I do this, something bizarre happens. We'll get to it. Or let's say I just move like in this direction. You know what I mean? So we kind of understand that. Move a straight line that way, or just move in a straight line that way. Alright, hell yeah, I just got to get to it, you know what I mean? So if we're on the Earth, we're spinning around. Anything that's spinning around a circle, on the outside, it feels like you have tangential velocity. Well, we don't feel it, but we're going like 1,000 miles per hour. And if we're on the outside of a circle, we really just want to go in a straight line. Like if you have a string and then some sort of mass on the end of it and you're whooping it around, and then all of a sudden the string breaks, and you know, it's going around in a circle. Well, the second that string breaks, this thing's just going perpendicular or a tangent to the circle that it was on. So at any given instant, that is the direction the velocity wants to go. But now something is constraining it to move in a circle. And then that definitely, and we're going to see what that does and what that entails and how it involves F equals ma, how it involves an acceleration, and how that changes maybe the force that you feel. Okay, and so here's my little proof that I like to do, is that currently right here I say I have no velocity towards the radius. So if I point an arrow towards the radius, I have 0, meters per second. I do this in meters per second. But guess what? If I don't have any velocity towards the center, well, just theoretically, I should just be moving in that direction. And that's what we want to do if the spring breaks. But that's not what happens. A little time later, I'm over here. So just between, like how did I get? And from this drawing, you can't draw it small enough, but it looks like I just moved that way. But technically, I moved in some sort of direction towards the radius. So keep that in mind. And what I like to do is make this really long. And this can still just be like 1 meter. And we can have an angular acceleration of 1 radian per second. You know what I mean? So visually, hey, didn't we say about 60 degrees? If this is the radius and then we're going around a circle, like if I measured this with a string, I would drape it to about there. That's going to be 1 radian. So cool, now we have a visual. This is such a good one to do. It's the proof that I use, because I'm not just going to use an equation if I'm not just 100% intuitive of exactly what's going on with it. And then there's some equations that I will use sometimes where you're just like, who cares? If they say this is the equation, I'm going to use it. But I think this equation is complicated enough, because then we have to actually throw it into the F equals ma part, and I just don't think it's super obvious like where you put it in and how you use it. Okay, so but yeah, we're gonna kind of derive this, and I think it'll be better if we change these up, because right now my acceleration is just going to be 1, and we're not going to understand why. 1 squared is 1, and then 1 times 1 is 1. So I guess we'll do it this way, and then we'll change these values up to make sure it is representative of omega squared, and then that r term. Okay, so if we're going 1 radian per second, it's going to look like this. 0, 1. So we just have a constant velocity all the way up to there. So what I'm going to do is say, whoa, let's do 1/100th of a second. I don't even know, you would have to count to 100 before someone's counted from 0 to 1. Like it'd be very fast. Okay, but if we're only traveling for 100th of a second, and it's essentially breaking this up into 100 pieces. So I'm just traveling that far, and I probably didn't draw my picture well enough. But so tangentially, I just want to go straight, but I know I'm bound by this circle that actually comes in at some sort of angle like that. And then I also know that if I go out to here into this circle, this 1 meter is the same as that 1 meter. Because I'm sweeping a circle. Anywhere that I'm out here, this is my radius and it's 1 meter. Okay, so now I draw this vertical part. So what I see is that now I use like just right triangles. I come down here and say this is perpendicular. Now you just busted this 1 meter up into 2 chunks. You said now this is maybe like D. You know, we're going to say that's like, you know, I'm just going to distance D. And then so I'm saying this 1 meter is 1 meter minus D. So see how the original radius was out there? But now because I came up here, dropped down that right triangle, I have this D distance. So now this distance remaining is 1 meter minus D. Okay, now if we throw an angle on here, then we'll know that, hey, the sun is shining. This is the sine component. I'm most interested in the cosine component. And so now I can say, hey, if this is my hypotenuse, then I'm going to say, you know, the hypotenuse, the bigger number, times cosine of the angle, you know what I mean? And cosine is just a fraction of this bigger number, is going to be this. Is going to be the radius minus that distance. Cool. So now I can, and then I know that this bigger number is the radius. So there's, you know, even this equation might be kind of difficult to, you know, I don't know, but it's just radius cosine theta minus D is equal to, whoa. I'm sorry. Oh, holy Toledo. So, okay. So if I'm doing it the way I'm doing it, I go radius and then cosine of that angle, that's going to equal this. And this is the radius minus D. So that's going to be equal to R minus D. You're not going to see it like this. What you're going to see is like, hey, I just want to solve for D. So I want to know what D is. Well, I'm going to say that's this radius minus this chunk. And that's going to be radius minus the radius cosine theta. So if I do it that way, it's just radius minus radius cosine theta. But you can see if we rearrange this, that's what we'd get. Bring the D to the other side. This R cosine theta to this side, and we're going to have D is equal to R minus R cosine theta. So this one comes up, you know, this equation, something that looks like this, can come up quite a bit. Alright, hell yeah. So, and what are we doing here? Well, I said that we have zero velocity towards the radius. We're basically doing just simple integral calculus. And then at some point here, like, so all my velocity is tangential, you know what I mean? And I know what my velocity tangential is. Finally, we get to use our equation. That's radians per second. Radians times radius is something normal. So we have 1 radian per second times 1 meter is our tangential velocity is 1 meter per second. Cool. But 0 of that, it's all going in this direction. None of it's going towards the radius. But at a small fraction of time later, of 0.01 seconds, we are over here, you know what I mean? So we moved towards the radius during that very fractional of a second. And we moved a distance D. So now you have to be very careful, because now we say for sure, we have a check on reality that we do have velocity towards the radius. But this is where you have to really be careful and say it's the average velocity, because right here I have 0 velocity towards the radius. So I need to figure out what my average velocity is, and I traveled for 0.01 seconds. So in that 0.01 seconds, I technically moved from here, like here to there, this distance D. So let's get an equation for average velocity. And this one's gold. It's just total distance divided by total time. You know what I mean? So you can even use this for a lot of different problems without getting too heady on some of the kinematic equations. And so I know that that's distance D divided by 0.01. And I know what D is. So now I can get average velocity is just R minus R cosine theta, whatever the hell that's going to be. That is a distance, and then we're going to have divided by the time, 0.01. Okay, now if you can just bear with me that this is a number, we still need to figure. I'm sure you're like, well, what the hell is the angle? Well, that's going to be determined of what our radians per second is. And we can kind of do that right now. So if I say I can sweep about 60 degrees, I know 60 degrees is about 1 radian. It's 57.3. You know what I mean? But if I know that's about 60 degrees, you know, in 1 second, well, I went 60 degrees in 1 second, but now I'm only going to go divided by 100. I'm only going to go for 100th of a second. So I only sweep out 0.6 degrees, you know what I mean? And we don't want this problem in degrees. We want it in radians anyway, because when we throw it into, it wouldn't matter anyway, because cosine of 0.6 degrees is super small. Yeah, and see how your distance is, so let's do it. So we're going to have 1 minus 1 times that answer, divided by 0.01. So we have a distance of 0.005 meters doing it that way. Now, we can just do radians and it'll be really simple. As long as you can trust that 1 radian is what we would span in 1 second, cool. Then in 100th of a second, we're gonna span 100th of a radian. You know what I mean? And so so we're gonna change our calculator to radians, and we're gonna have 1 minus 1 cosine 1 divided by 100. And cool, we basically get the same thing, 0.0049, bunch of nines, and that's basically the same thing. Oh, was I off by a factor of, no, this is 0.123 zeros, and then a 4. So we got 1, 2, 3, 4. No. This is 3 zeros. 1, 2, 3 zeros, and then a 4, 9. But why was I off by a 0 there? Let's go back to that one. What was I saying? This is about 60 degrees, and then divide by 100. We got 0.6. Go back to my calculator in degrees, and we're going to do 1 minus 1 cosine 0.6 divided by, no, that's the distance. Yeah, so yeah, I must have made an error somewhere. So doing it in degrees, we get 0.1234 zeros, and then a 5, 4. But that's wrong, you know what I mean, because 60 degrees isn't 1 radian, you know what I mean. So 1 radian is 2 pi 360 divided by 2 pi. That's 1 radian, 57.29 degrees. Okay, let's focus, because we're basically close, you know what I mean? So we have our distance. That was going to be r minus r cosine theta. And we have 1 minus, and let's get into radians. Now that we know what we're doing, we can do it at light speed. 1 minus 1 cosine of 1 divided by 100, because that's our angle. That's 100th of our angle of 1 radians, because we're going 100th of a second. Okay, now that's our distance. Now we're going to divide by 0.01, which is our time. So now we have distance divided by time. Again, that's average velocity. Cool, so I'm going to store this as alpha v. So now we have an average velocity, and this is the average velocity that we're moving towards the radius. But here's where kind of the calculus goes, and I always draw this. If I'm going, this is a cool one. 1 hour, and I'm going 0 to 60 miles per hour. It's a bizarre one too. It'd be like if I'm driving for an hour, but I slowly increase my speed to 60 miles per hour for an hour, and then maybe get to my destination. The question is, like, well, 2 questions. Like, what was my average speed? Well, that's 30 miles per hour. And then what's the distance I went? Well, I went my average speed times 1 hour. I went 30 miles. So that's the same thing we need to do here. We're going 0 miles an hour towards the radius, but then we just found out this, actually. We found out our average velocity had to be 0.005 meters per second. So what we want to do is this top end to actually make that average velocity. We know we're going 0, and we know what our average velocity needs to be. So this top end is just 2 times. It's just a factor of 2 times the average velocity. Sweet. So we just multiply by 2. And this is like, you know, kind of area under the curve stuff, or blah, blah, blah. You know what I mean? You don't need to know too much about physics, but I mean, you do need to know that if I'm going 0 miles per hour, and then I'm slowly increasing to 60, it's for sure, I for sure am not going 60 miles per hour the entire trip. And I'm for sure not going 60 miles. So you can just see by basic geometry, it's a very good geometric representation of what's going on. Okay, hell yeah. So now that we know this max velocity, or the velocity at this point towards the radius, is now just 0.01 meters per second. And then we said our alpha v average was just half that. Cool, at 0.005 meters per second. Okay, so now how the hell does this relate to acceleration? Well, that's what we're going to do right now, because acceleration, by definition, is change in velocity, change in time. And I love doing F equals ma stuff. Especially if you can take like accelerations at specific points. Even if I have to throw it into Excel, this is magic, because we have this equation that's very magical. It says if we can identify a mass, and that's going to be us, we're like on the surface of the Earth, and then we're spinning, you know what I mean? And if we can identify that there's a change in our velocity, because if we're spinning around the Earth, we all know that our velocity tangential is the same. So then the question arises, well, how am I having a change in velocity? Because if I'm having a change in velocity, that means there's an acceleration. And if I'm having an acceleration and I'm a mass, then F equals ma applies. It means that there's going to be and I'll say it this way. Instead of saying it in the centrifugal way, there's going to be a net force trying to throw me off. It's like, no. I have to stay on that ride of an Earth. I have to apply a force towards the center to do what we're doing. You know what I mean? So that's the centripetal. That's the actual force, the centripetal force. To stay on a circle, you need to apply a force to hook yourself into the circle. If you do not apply that force, you will just be moving tangentially. And so that's the true force. And then we're going to see why the force that we're adding into, anyway, for whatever reason, because of these two terms, and the different ways of thinking about it, it can easily get me overwhelmed and confused. But anyway, so what we're doing is we're finding this change in velocity, change in time, we're kind of deriving this. So now we had zero velocity towards the center, and now we have a max velocity towards the center. Well, booyah! Let's break out our equation for acceleration. By definition, it's change in velocity, change in time. So we have a change in velocity. We went from 0 meters per second towards the center of the circle to a whopping speed of 0.01 meters per second towards the center of the circle. Cool. So our change in velocity is 0.01 seconds, and we did that in 0.01 seconds. You know what I mean? So I'm sorry. Our velocity is 0.01 meters per second, and then we did that divided by the change in time of a hundredth of a second. Holy hell. And then so that's going to be an acceleration of 1 meter per second. And if you write it like this, it's just, this is 1 meter per second squared, but it's a change in 1 meter per second every second. Alright, so I don't think you totally trust and believe me, because this says, well, omega should be squared and radius should be what it is. So let's throw something that we would actually get something cool. So we're going to throw in 5 radians per second for our angular speed, and 5 squared will be 5, or will be 25. And then what do you want to multiply by 5? Let's try to get 100 out of this. So we're going to take our radius to be 4 meters, and then our angular speed to be 5 radians per second. Okay, heck yeah. So now what we need to know is well, one is kind of like how far, what angle did we sweep? And we're going to do a hundredth of a second. So we're going 5 radians a second. So we're going, so here's 60, there's 60. I mean, basically, it's almost a full circle 6 radians. You know what I mean? So we're going, this full, about to here in 1 second. So we go 0, 1. 0, 1. But if we're out here, we're going 0, 1, 0, 1. So that's kind of the speed we're going, and that's very useful, because in a hundredth of a second, we're going to have And this spells it out. Like angular speed says, hey, and yeah, because there's a few, every equation looks like this. You know what I mean? If you want to know what velocity is, well, that's change in position, change in time. You know what I mean? So writing your equations like this is just gold, because now we can see that angular speed is a change in our angle in radians per, you know what I mean, change in time, or 1 second. So 5, this says we're gonna, for every 1 second, we're gonna go 5 radians. Well, we're not gonna go for 5 seconds. We're only gonna go for 1/100th of a second. So that's 1 divided by 100. Oh, and I totally did that wrong. Holy, you got to get units on this. You know what I mean? So this says that radians per second. So we know what our radians per second is. We know what our time is. So even here, anytime you get something like this, this is an equation of 3 terms. You can rearrange this equation any way you want. So what we want to find is the angle in radians. So that's going to be angular speed times change in time. And another way to do it is just throw the units on here. We have units of radians per second for one of the terms. We want radians, and we have this seconds term for our change in time. What we have is 5 radians per second, 100th of a second. What do we do to these two to get radians up top? Well, we just multiply them. And so seconds cancel and we get radians. So that was just like about 3 different ways to get to the same thing. And because I just made an error. I just took 5 and divided it by 100th of a second. And that was horribly wrong. We want to take that 5 radians per second times 0.01, and to get, so that's going to be our angle in radians. You know what I mean? It's going to be not just 100th. It's going to be, if you divided this into 100, it's going to be 5 of those. You know what I mean? So if you divided this into 20, so this would be 5, then we'd go 1. So we'd do, yeah. So we're basically right there. So visual representation is pretty darn close. All right, so hell yeah. So I think that was probably the hardest thing, just to be like, hey, what's our angle? Our angle is 0.05. Angle 0.05 radians, and now we can just plug and chug. What the hell is our distance? It's going to be our radius, 4 minus 4 cosine 0.05, and we have to be in radians. We are. And so that's going to be our distance. Our average velocity, you know, definition average velocity, change in distance, change in time. And then, so we're doing the same time frame, just 0.01 seconds. So now this is our average velocity. It's much higher. We're going 0.5 meters per second. So, but just our scale is way different. Like this is 4 meters. So if this is 4 meters, like this is 1 meter. So this is 1 meter per second. You know what I mean? So there you go. So get some representation on it. If that's our average velocity, we know from that integration kind of trick that times 2, or from this model, times 2 is our max velocity. Cool. So now we're going to know our change in velocity, and we know our change in time still, and that's the definition of acceleration. So now from here, we're going to see that our change in velocity is this, 1 meter per second, and we do that in 100th of a second. That's amazing. Cool. So from this model, we see that our acceleration was our change in velocity of 1 meter per second divided by 0.01 seconds, and that gave us basically equivalent to 100, or 99.98 meters per second. So this is our acceleration. So that kind of proves this equation, and now we can move on to the next step. Hell yeah. Alright, hell yeah. So we're back. And now we found out that there's going to be an acceleration, you know, in both these cases. And then this negative sign, it says towards the center. And you know what I mean? I'm honestly not intuitive, because you have these two terms, centripetal and centrifugal. So what we're going to do is, because these accelerations are meaningless to us, we want to make it the Earth and then us on the Earth. And then we're going to find the acceleration of us, and then that's going to affect maybe like how much our weight feels, or you know how much. And so we're going to set it up with an example where we want to understand this acceleration, you know, the centripetal part, the true part. Okay, sweet. So we're just going to do the Earth and then we're going to be on the end of the Earth. This is North Pole, we're looking down, so we do have some sort of omega. And now we want to figure out, that's the first thing. You're like, we've been talking about radians per second, and if this is the radius, we're going to be to there in a second, there in a second. If we're going 1 radian per second, and we'd go around 1, 2, 3, 4, 5, well, there's 6, sorry about that. And then we'd go around 6.28 times. 6.28 radians is equal to 360 degrees. And so if you use the factor label method, I kind of in my intro to, or basic math video, I don't like this, you know what I mean, stack these. If you have an equivalence, stack them, because that, and I've never done this before, because I don't like converting between radians and degrees. It seems like it's going to be confusing. But we have, this is how many radians are in a circle, so we have 360 degrees. Cool, and you can just stack it the other way. Just so it's at the ready. And I think this is a good way to do it, the 6.28. It's better for your brain to know that there's about 6 radians in a circle than the number 2 pi. But obviously it's the same thing. 2 pi radians divided by 360 degrees, and then just the opposite. But man, I think anytime you see the symbol pi, you're just like, no, not for me. Okay, so now we need to figure out what this value is. And so that's why I did this, because we don't know what radians are. You know what I mean? We know what full circles are. When you turn on your drill, you're like, hell yeah, isn't that 1,000 revolutions per minute? And so this is the one that I always go to. Well, let's do this factor label. And even this is just like, ooh, 1,000 revolutions per minute. That sounds real fast. Well, how many revolutions is that a second? You know, I mean, we throw 1 minute up here, and then 60 seconds down there. And you're like, ooh, we got to divide by 60. So it's not that many revolutions per second. It's still impressive, you know, 16 times a second. So now we have 16.6 revolutions per second. Now, how do we do? And then, I don't know, I don't think you need to do a factor label that 1 revolution is 360 degrees, but maybe, you know what I mean? That's probably why, you know, the headache, I remember just being in college and being like, oh, I hate this. Converting radians to degrees and degrees to radians is like, no, thank you. And just at the end of the day, I just feel like no one had a good grasp of what a radian was. Okay, so, but here's another, these two things are equal. So, you can use them in your factor label method. I see revolutions. Cool, I see revolutions. I have to have the revolutions downstairs to cancel it, so let's do that. So 360 degrees is 1 revolution. Okay, and even this will be a nonsensical thing to do, because we'll have degrees per second. I mean, it won't be super nonsensical, so we're going to have times 360. So this thing is going to go 6,000 degrees per second, but at least you have a visual of that, guaranteed. Even though no one really knows like what 1 degree is, like we know what a circle is, and we know there's 360, and so if someone says 6,000 degrees per second, I don't know, it just feels right, you know what I mean, it feels comforting. But if someone says, and then, because now we're going to do the factor label method and actually get to radians, but you shouldn't do that. The first thing you should do is like, well, can't we guess? I'm going 100 revolutions in a minute, and then you got to think like, what's a revolution? 1 revolution is 6 radians. So even just right at the problem get-go, 1,000 revolutions. How many radians is that going to be? Well, 1 revolution is 6 radians. I mean, it is so bizarre. Like, I'm spelling it out not for you, but even for myself. It's like, I got it now, but okay. So it's going to be 6,000 radians. So now, anytime I see this term of revolutions, I can be like, heck yeah, that's going to be, you know, just times 6. You know, so perfect. So now, this is going to be 6,000 radians per minute. And then you could easily probably get to radians per second. Because if it's 6,000 radians in a minute, divided by, you know, 60 seconds, is 6,000 divided by 60. Isn't that like 100? You know what I mean? Because the 6,000 divided by 6 would be 1,000, but then divided by the 10 part, that's 100. So basically, yeah, this is a good one to do. 1,000 revolutions per minute is about 100 radians per second. And let's double check that. Did I do that right? Just on my quick calculator, you know what I mean? Like 1,000 times 6 is about how many radians there are divided by a minute. And I'm going to factor label that divided by 60. So I should have about 100 radians per second. And that's kind of just a cool equivalence that a lot of people probably don't, don't get, because it's not right. I mean, there's 6.28, so if we did that, 1,000 times 6.28 divided by 60, divided by 60, we're going to have 104, but who cares? Close enough, right? And then so let's do the full factor method, factor label method for our drill, power drill going 1,000 revolutions per minute. Factor label method would be like, hey, we need to cancel minutes, and we know that that's going to be equal to 60 seconds. All of these are equal to 1, I don't think you need to know. I mean, obviously they're equivalences, but you're just worried about just crossing out units and making sure that you're left with the units you want. Hey, we got to seconds. Cool. Now, revolution. 1 revolution, 360 degrees. Cool. And then 360 degrees. And I would write it like this for your first few go-arounds. 6.28 radians is, and then when your calculator, just know to do 2 pi to get hella accurate. Okay, degrees cancel, and now we're left with radians per second. So we're going to do that. 1,000 divided by 60 times 360. And I love doing this with my calculator. I don't want to put in all these parentheses. You don't need to. It's going to do 1,000 divided by 60, and then you can just instantly go to multiply by 360. This is not going to put everything downstairs once you do a divide. If you do a divide by on your calculator, it's only going to put the next thing downstairs. Okay, cool. And then we got times 2 pi divided by 360. All right, hell yeah. So we got that 104.719 radians. And we can visualize that. And this is radians per second. Because this next thing sucks. We can't visualize it. Because now we're going to do the spin of the Earth. And, we need to know a time factor, seconds, and we need to know radians. But even right here, maybe we don't like radians, and we just know, hey, I like to work in revolutions. I know what 1 revolution is. Cool, and I think we know what 1 revolution is of the Earth. We know that that's called 1 day. And I think we know how much time that takes in seconds. You know what I mean? And so, and I said I didn't want to do every proof, in here. So for this problem, we're just going to say it's 24 hours. It's not. The Earth, for 1 rotation about its axis, is minus 6 minutes. And let's say I didn't know that. Let's say let's say I messed that up and I thought it was minus 4 minutes or minus 6 minutes. Oh, damn it. I just can't help myself. So we are going to do that. It's because it's just it's so good for me to. So here's the sun, here's the Earth. So my knuckles this is high noon, and hell yeah, you're just right there. Okay, so just imagine a day rotates, and then we're back. You thought that was okay. We're just gonna call that a day, quote unquote. But then in a day, I'm rotating around the sun. So look at that. So I win a full revolution. And then I went over here. So look at where you're pointed. You're not pointed towards the sun. You have to rotate a little bit more for your high noon to match your, So this means that if you call this going 1 revolution of the Earth and then going up here and then turning a little bit more to what you think is, again, high noon, what happened to the Earth is it rotated once and then had to rotate a little extra, and you're calling that 24 hours. Now, even this is a problem unto itself, because you're saying, okay, the rotation of the Earth plus a little bit of extra rotation was 24 hours. So let's do that. So the rotation of the Earth plus t extra, I'm just going to say plus t, is equal to, 24 hours. So this means that the rotation of the Earth happens faster. It's just 24 hours minus that extra rotation. I'll just say it's that. Okay, so that means that the rotation of the Earth actually rotates faster. Now we need to figure out what that extra rotation is, but those extra rotations are additive. So if we went around the sun like in like 4 or 8 days, it would look like this. We would rotate once, and then we'd rotate, you know, to like an eighth of a turn, and then we'd rotate another time, get to here, and then we'd have to rotate. Hey, we rotated a full quarter turn, and then my arm can't handle this, but you'd go over here, and then you would if I got a quarter of the way around the circle and I did an extra quarter turn, that means once I go all the way around the circle, the Earth spins on its axis one extra time. And it's just phenomenal. Because we know in 365 days, you know, that's high noons. There's 365.25, you know, high noons in a year. And so, we just know the length of a year, you know what I mean? You know, even if you don't know anything about rotations, like the books are saying, a year is 365 days, and a quarter of a day too, because we have leap year. We all know that's like a celestial year, but now we want to figure out how many times the Earth rotates. And just from the commoner's perspective, well, wasn't there 365 days? Didn't we rotate 365 times? Sure, but we also did that thing going around the sun, so we rotated an extra time. So we rotated 366 times, and you definitely have to include this quarter of a day if you're talking about a celestial year. So the time that we rotated, maybe you don't. Maybe that's included. Let's work out the numbers. So we're going to go 365, and we want to figure out what's 365. So 365.25 days, factor label method. 1 day is 24 hours, and then 24 hours is 1 hour is 3,600 seconds. That's a quick one to do. And now we have the time in seconds. 365.25 times 24 times 3,600. So this is how many seconds are in our celestial year. So now we have the time in seconds of our year, but now we want to figure out our rotational speed, because now we're saying that we rotate 366 times in that amount of time. So I forget what the factor label method on this, but I think we just take this number divided by 366. I'm sorry I don't have a better answer for you, but we have 86,222.95 seconds, and this is a day. You know, if we took this number, our total time for a celestial year, and divided by 365.25, so that's where we do. I think officially we have to do this divided by 366.5, I thought. So yeah, we'll try to save that as time S, and that is time T. That's why I don't want to go down these tangents, but it is good because we want an accurate representation of the spin of the Earth. And so what is this in hours? So we're going to go 3,600 seconds is 1 hour. Cool, so we just got to take that divided by 3,600. So one of them is 23.95, and then the other is divided by 23.91. So minus 23 times 60. Alright, hell yeah, scratch all that. That was so stupid, you know what I mean? And I think this like 0.25 days got me confused. I mean, that's why you don't get too detailed and when you're just trying to find like an example of something. So what we're saying is that in 365 days, which is times 24 hours, in that many hours, we are spinning 366 times. So we just divide that by 366, and this is the hours. This is the hours of a day. Damn it. Alright, hell yeah. I don't know why that was so hard, you know what I mean, because we can do that. So 365 times 24, this is how many hours, and then we divide it by, because we're actually spinning 366 times, just to get a ballpark. And so yes, this is the hours of a day. It just looked funny. So I did 24 minus that, and so this is you know, that the time less. So we know that we're spinning faster. A day isn't 24 hours. It's just a little bit less. And this is how much it is less, times 60. So it's 4 minutes less. So this was the right answer. The Earth spins 4 minutes less. So a day is 23 hours, 56 minutes. That's where kind of like I get confused with the 6. Is it 4 or 6? But it's 56 minutes. And even this, 4 minus that, you can kind of divide by 6, now multiply by 60, and you can see that it's, oh yeah, this is interesting, because I think the textbooks say it's 9 seconds. I think I remember that from like Wiki, but just from our rough estimate, we only got extra of 4 seconds. So what gives? Well, it's because we're not adding that like quarter of a day in, so 365.25 times 24 hours. And this is really close. Like a day, like an actual high noon to high noon, it just happens to be. It just happens to be 24 hours. You know what I mean? We didn't set that. I mean, we set our time based on like a cesium atom, you know what I mean, or whatever. We hella did not set our time in seconds based on a high noon to high noon day. So yeah, that 24-hour mark can change and will change as we go on in future. Okay, so here's going to be a better representation of the hours, and now we're going to divide this by 366. What do we do at 360? Or what do we do 366.25? That's where I'm kind of confused, but I think we would do 366.25 minus that answer, and then times 60. We have the same 4 minutes, but then we're going to go 4 minus that answer, and then times 60. Or maybe it is. Maybe I'm wrong. Maybe it's 3 hours, 54 minutes, and 4 seconds. I don't think so. I swear it's like 9 seconds. And I don't know. I mean, but you'd have to get real hella techie to figure out exactly what's going on. You know what I mean? That last quarter of a day, well, you're not doing the full anyway. But at least, you know, just using rough idea of what's going on, you can at least for sure be 100% positive that the Earth spins 4 minutes faster than what we think is 24 hours. It's 23 hours, 56 minutes. So we're just going to use that for a problem. We're going to go 23 times 3,600 plus 56 times 60, and this is the time I'm going to use. I'm going to say that the time... Alright, so the time in one rotation of the Earth is going to be 86,160 seconds. So we have that, and we know that that's 1 revolution. Cool. Don't we know that's equivalent? You know, if we do our stacking factor label method, 1 revolution is 2 pi radians. You know what I mean? If we're getting ahead of ourselves, let's write at 6.28. So now we can... and then even here, just stack them. You know, this happens in chemistry a lot. You're just like, oh man, I don't know what to put on top or put on bottom. Who cares? Just guess. So we're going to do this, and then we're going to do 1 revolution. I'm not even worried about what I'm trying to get. You know, I'm just gonna do it on the fly. But I do know that 1 revolution is 2 pi radians. So cool. I just converted to radians. And now I have something that's seconds divided by radians. And now the light bulb goes on. This is the way my brain works. I can't think of everything at once. So it's just like, well, that's cool. That's what I wanted. I wanted this angular speed in radians per second. It's just upside down. So it's okay to do this. You know, even if you were doing like a test, you would just do this and then just invert it, and then you would have radians per second. So let's do that for this one. 8,600, divided by 2 divided by pi. So this, if you do no parentheses, heck yeah, you got to do this divided by 2 and then divided by pi if you're going to do it with this method that I like. And then we're going to have, yeah, so that's that number, and it's like we got to invert it. And now you get this classic. And if you've not done this, so yeah, or just take your time and go, cool, I need to flip this initial thing. 1 revolution is 86,160 seconds. And of course, my answer wants to be in radians per second. So doing it like this makes sense. And then 1 revolution is 2 pi radians. Radians cancel, and we get revolutions per second. So this number is going to be 1, 2, 3, 4 zeros, and then 7, 2, 9. You know what I mean? It's a sucky number, but this is how many radians per second. It's 7.29 times 10 to the negative 5 radians per second. So now we can go back and set up our example. You know what I mean? Hey, let's take a change in time of 1 second. So we have that. We know the radius of the Earth is like 6.37 times 10 to the 6, or basically 6 million meters. You know, that's the radius of the Earth. And we can use our equation to find the distance towards the center of the radius that we're going to be traveling. We can find our velocity towards the center of the radius. We can find our average velocity, find our max velocity. We know that acceleration is that, you know, basically the change in velocity, which at this point we have 0 velocity towards the center, so it's just going to be that max velocity divided by our change in time. And if we use a time of 1 second, it's just going to be, you know, basically our max velocity towards the radius. All right, hell yeah. So let's set that up, and we'll do this again. You know what I mean? Here's our d. Here's the radius of the Earth. This is radius of the Earth minus radius. Holy Toledo. No. Like d. D is the radius of the Earth minus radius of the Earth cosine theta. So this part is just the radius of the Earth cosine of our angle. Okay, but then we have that same thing as like, what's our angle? So our angle is going to be in radians, and but hey, we know our angular speed in radians per second, and we're going to do a change in time of 1 second. So this is, by definition, I'm going to store this as alpha w. This is going to be how many radians we're going to be traveling. Let's get our equation out. You know what I mean? Is negative r omega squared. Our acceleration, we can just do this right now. This is 6.37 times 10 to the 6. That's going to be in meters, radius of the Earth, times this 7.29 times 10 to the negative 5. So, and this is alpha w in my calculator. I'm going to do 6.37 times 10 to the 6. I'm going to store that as alpha r in my calculator. So now we have alpha r times alpha w, and we have our, what did we just find? No, we got to square this. Oh, this is a tiny number, radius. We're going super slow. The Earth is moving slow, you know what I mean? For all purposes, the Earth is hella slow. And I apologize I didn't square that. So we have alpha r omega squared. And we get an acceleration of 0.0339. And this is a check on reality, and this is meters per second squared. Because, yeah, this 0.03 comes up a lot. The acceleration towards the center, the acceleration of, I mean, just in general, that term acceleration, because we've heard of the acceleration of gravity, is 10 meters per second squared. And so this is much less. So then the question is, well, it's like we know from centrifugal things, they fly outward. So is this how much less we feel? Sure. So the intuitive thing is be like, well, instead of feeling 10 meters per second squared of gravity, we're gonna experience the gravity that we feel at the equator is 10 minus 0.03. So that's gonna be 9.97. Or if you did 9.98 or 9.81, sorry, for the acceleration of gravity, we'll use that too, and then subtract. Yeah, you're gonna get 9.81 subtract 0.0, just that second answer, and you're gonna get an acceleration of gravity of 9.776. So that difference is the weight you will feel differently. And let's just get our F equals ma. If I weigh 70 kilograms and the acceleration is 0.039. The force on my body is 70 times that answer. And the force on my body is 2.37 newtons. And you got to divide that by 4.44. So yeah, it's half a pound. It's 8 ounces. So I will feel 8 ounces less at the equator. But see, that's the intuitive rationality that I use to get there. I still struggle setting up the free body diagram, but we're going to do that. We're going to go the full distance on that. I thought this was going to be a 5-minute problem. Hell no. Alright, hell yeah. So now we're at that transitional point where I think we can make this make sense, because I like to use the example that we're just floating in deep space, and then all of a sudden a string with a sign that says, you know, hang on, you know what I mean? And this string is attached to a fictional place. It's just pinned to the universe, you know what I mean? No stars, no nothing, you know, no gravity, no nothing. We just have a chunk of mass, that's us, and now we grab on to the string, and this string just happens to be the radius of the Earth. Okay, and guess what? We're traveling at a tangential velocity. What's our tangential velocity? We got to do that radians per second. That's something weird. You know what I mean? Radians times radius is something normal. And so we know that omega in our calculator. That's a horrible looking number of 7.29 times 10 to the negative 5 radians per second. And then we're going to multiply by the radius of the Earth. We have that in our calculator as 6.37 times 10 to the 6 meters. Cool. Doesn't this give us tangential velocity? Alpha omega times alpha r? Hell yeah. And we're going 464.5 meters per second. I don't know what that is, but using my axiom of times 2 times 25% tip, we're going 1,145 miles per hour. Now, it's like times 2.23. Is it 2.23 or 2.234? I have no idea, but you get it. We're going 1,000 miles an hour. That's crazy. So we're going 1,000 miles an hour and we grab on. Now the question is, my question is like, hey, is there going to be tension in the string? Sure there is. So now we have to do F equals ma. And there's two sides of this equation. One is like, hey, what do we see? Do we see motion? Because if we're doing a bridge, we better not see motion. You know what I mean? We throw our eyeballs on the bridge, and we're like, okay, there's no motion, there's no acceleration in the y direction, in the x direction. The bridge isn't twisting about any axis. We don't have any motion at all. Hell yeah, check on reality if you're building bridges. Okay, so that's this side of the equation. I'm identifying a mass. The mass was the bridge, and I want to know, like, is it moving? Cool. And then this side is that if we have a mass that is accelerating, there must be a force, you know what I mean? And so that's what we have. And I guess we have to cover all our bases, because if we're on the Earth and we're just like, well, and we do that, yeah, well, I guess let's do this one. So we have, well, maybe not. Well, I mean, there's like 3 of them you can do. Like, one is just jumping off a cliff. So if you jump off a cliff, you know what I mean, there's your mass. Hell yeah, you're moving. And we can calculate how far you're moving. You know what I mean, how far, and then at what time intervals, like you got to there. And then so that was this side of the equation. Well, we identified the cliff jumper. We see that they are accelerating, check mark. Now we want to know does this one make any sense at all? Like what the force on them is? Oh, that's so bizarre. That's like the definition. Because what I do with free body diagrams is like, well, we'll take that mass and put it into outer space. So now we just go into like deep space, and now we're going to do that same thing. We're going to say, hey, this mass has an acceleration. I usually do it the opposite way. I usually say, hey, this mass has a force, and that's what we do in statics and stuff. But I can put a little arrow that says, hey, we're accelerating in that direction. We are a mass. And so the F equals ma equation, the only way for this thing to accelerate is there must be a force on this mass, and basically in the same direction as acceleration. So there must be a force causing this to accelerate. And so that comes to this side of the equation. And the forces are just the forces in the known universe that we already know about. You know what I mean? It's Fg. It's the force of gravity. So let's do that one. Force of gravity is gravitational constant, mass of u, mass of the Earth, radius of the Earth squared. Well, and we've got to step back. The force of gravity, and then we go back to our picture. You know what I mean? Why is there a force of gravity? Sure, we have mass, who cares? Like literally, who cares that we're made of mass? Who cares? But we have this relationship that says if you're next to any other mass in the universe, and we got the Earth underneath us, it's huge. All right, this equation says there's going to be a force on you. And so cool, there's a couple we're doing the kind of two different ways to look at the F equals ma equation. And yeah, I usually don't look at it like this, and I think that's my main error. It's like I'm not looking at this as like a mass that's accelerating, and then therefore there must be a force. I always look at it as like, okay, I know that my mass, I know that I have a mass, you know what I mean, that it looks like this, and then I just know that there's a force on me of gravity. You know what I mean? So both get to that same thing. So yeah. So if I did this one, chop that out of deep space. Well, it's just like, and I know that I am a mass, and then I see, hey, there's no other forces on me. You know what I mean? There's in the known universe, I know that there's not like a normal force. I'm not just resting on the Earth or something like that. We'll get to the normal force in a second. But I do know that, hell yeah, there's this Earth that's just right there, and I'm right there. And so there's going to be a force of gravity. And it doesn't even matter if I'm just standing on the cliff. That force of gravity is always going to be there. If there's two masses, there's going to be a force trying to force them together. Okay, sweet. So, and that equation says this force of gravity is the mass, because that's why that's important, and then gravitational constant, mass of the Earth, radius of the Earth squared. I'm just going to make this a little bit quicker and just say, hey, that's this. You add those three things up, and that's 9.8, 9.81. That's 10 meters per second squared. You know what I mean? All the same thing. And so you're going to have a force on this of gravity. All right, force of gravity that's equal to the mass times the acceleration of gravity. Cool. And oh hell, you know what I mean? And even that's skipping steps. You know, if you did it textbook, you would say, okay, I'm identifying a mass and I want to know its acceleration. This A is what I want to solve for. And then so I say, you know, it jumped off the cliff. There is no other force. There's not a force of drag because, you know, it's who cares? There's not a force, you know, like you're just jumping off a cliff. Drag is so meaningless. You're still going to be going 50 miles an hour once you hit. It sucks. Okay, so let's say this is the only force we've identified. So then we say the force of gravity is equal to mass times the acceleration. Leave this A alone and say solve for that A. You know what I mean? So, and you could do this in a couple ways. You could be like, hey, well now let's just throw this equation in. You have G, M, me radius of the Earth squared is equal to mass times acceleration. You could do it that way and then solve for acceleration. Well, now we're just going to divide by the mass and the masses cancel, and we're going to get acceleration as g me radius of the Earth squared. Cool. Or just do it right now. Let's solve for acceleration. That's force of gravity divided by m. And then the same thing. Force of gravity is g me radius of the Earth squared divided by that m. M's cancel, and you get the same thing. You get acceleration is these three terms, and that by definition, and you get something like this. This acceleration is what we're called. These three terms are called this letter g. So the equation is your acceleration for this problem is just equal to g. Cool. So, because I swear, like it took me a while to be like, whoa, well, let's turn this into a story where you have two different sides. This one is for sure what you're observing the mass doing, and sometimes that's what we're interested in. Sometimes we're just like, no, this acceleration is zero, so we're just interested in maybe more into this side in statics. Okay, so now I think we should be able to let me take a pause. Alright, hell yeah. So I think I know where I want to go with this. So, and because the other thing is, hey, you might be standing at the bottom of the cliff waiting for your buddy to jump into the water or something. So if you're doing that, you're a mass, and then what we can do is the F equals ma. Now in this situation, well, we're not just airborne. You know what I mean? So we can identify the mass and be like, hey, are we moving? The eyeballs on it? And we can be like, no. So our acceleration has to be equal to 0. Okay, but then we go to the the known universe of forces and be like, well, don't we still have the force of gravity? So yeah, obviously. So what is this saying? Isn't that saying the force of gravity and then mass times accelerate? Well, isn't acceleration 0? You know what I mean? So how does this thing work? You know what I mean? Well, this is well, let's try to chop it out. So we're going to chop this out, throw it into deep space, and we observe that no motion. The acceleration is 0. But then we've already identified one force. We've identified the force of gravity. And so this is the cool thing about experimental physics is like, well, then you can conclude. You know that F equals ma is like, just kind of the gold standard. Anything that actually has known mass, like particles of mass, more or less will obey F equals ma, as long as the masses don't just go, so tiny you get into quantum stuff. Okay, so, but this says that if you, don't have, like, this is a mass, and if you don't have an acceleration, well, then, but you've already identified one force in a direction. I mean, by definition, if you've identified a force on a mass, it's going to travel that way and accelerate. It's going to change in velocity that way. But because we observe that we don't see that with the person standing on the ground, then it just has to be that there must be an opposite force that's equal to that force in that direction. And so there you go. And then we just label it N for normal force. And I don't know, maybe they should label it something else, like the fantastical force. I don't know, because it's nothing but normal. I mean, it just pops. It's like magic where it pops out. It's like the magical force. I don't know, but it's the only thing that makes this continuity where it's just like, hey, we observe no motion. The only way you can observe a mass with no motion in the known universe, especially since you have so many stars and planets, on it, like, it is a mass, and we know that there's other masses out there. And if all you know for your force equations, from the textbook side of this side, well, definitely G, the mass of whatever you're doing, the mass of the other things, the mass of the Earth and stuff, and then the radius or the mass of the stars. G, mass of U, mass of the stars, divided by the radius of that, between the distance between you and that star squared. That is going to be the force of gravity. So the fact that you can't escape being around other chunks of mass means that you'll have a force towards that star. You know what I mean? And, towards this star and, planets and stuff. And I guess from the relative perspective, sure, we might be moving towards those planets, because it's hard to, especially when you're just on Earth, you don't know if you're accelerating towards other things, but in the Earth reference frame, you at least know, you're in this direction. If this is the surface of the Earth, you're not sinking into the Earth. You know what I mean? So from that perspective, you're not moving in that direction. And so this should apply. But I mean, the light bulb should go on right now that yes, you are. We already said that there is this idea that you have a velocity towards the radius of the Earth. But the cool thing about the Earth is it's spherical. So you can put yourself on top. You can go to the North Pole and you're not going to be experiencing this centrifugal, like getting flung off effect. So that's kind of cool to put some perspective on it. All right, so we have this normal force, and so we have to identify that that's a force. We go back to our F equals ma. This is identifying the mass. Hey, we're observing acceleration or trying to find it based on an equation. Over here, for our problem, hey, this is 0. We already know that there's a force of gravity, so we must have to have, maybe adding a normal force. So now we're going to have force of gravity plus a normal force is equal to 0. Well, you can already see that I kind of wrote this wrong, where it's just like you can't have a positive number plus a positive number and get 0. So, one of these is negative, let's say the normal force. And that just says the normal force is in the opposite direction. And then, so a few examples of normal force, I guess we should at least do this one. So if my mass is 70 kilograms, and I know gravity is 9.8 meters per second. What this was mg. We know that's the force of gravity. That's the fast way to do it. And then we know that F equals ma. There's zero acceleration in this direction. In the y direction. Forces in the y is equal to mass times acceleration in the y. And so we're going to, over here, just identify that we have a normal force. And so we have negative mg, that's going to be down, and then we're going to have a normal force up, plus n is equal to mass times our acceleration, and that's 0. So now this is 0, and we have normal force is equal to mg. So this is just defining Newton's, second law or whatever, that equal and opposite forces. The force, if like the Earth, it feels your weight. Anyway, I don't know how to say it, but yeah, the force that you put on the Earth is the same mass times gravity. All right, so now let's go back to our string. We're floating in deep space. We're going to grab our string. We did this because we need some sort of representation of free body diagrams, and so we're going to chop that little block. And then we know that there's a tension, because it's a string. We know a string can't take compression forces. Okay, so we know that. So there's either going to be a tension in there or there's not. So we have a tension or there's not. And I guess one, I don't know, like, if this end of the string isn't attached and it's just a kind of a short string, and then you grab it and you're going this way, well, maybe there's not any tension. I don't know. But the fact that this string is fixed, and that'll kind of identify where the tension comes from. Okay, so now here is our free body diagram. We chop this. We're already in outer space, but we have identified a mass. We chop that, further into outer space, and then now we just put the mass and the forces. So we have the scenario. So we go F equals ma. What I like to do is like, hey, what's happening in our scenario? Just like the cliff jumper, like when we jump off a cliff. Hey, are we going to observe? Is our velocity 0 the second we jump off? And then do we have some velocity at the bottom? We've already identified a change in velocity. We kept it real simple, that there must have been an acceleration. You know what I mean? Absolutely. Here, it's not so obvious, because we know that we do have some sort of velocity, but we don't know if that velocity, we're trying to find changes in velocity. If we find change in velocity, then we've identified acceleration, and our F equals ma equation applies. Alright, so this is why, I mean, I didn't mention it in this video, but I consider this hidden acceleration. This is something that's not obvious. For circular, I forget, what do you call it? Polar coordinates, acceleration in polar coordinates. There's some that are just obvious. You know what I mean? You can have a drill where something's spinning around the drill, or like your saw itself is spinning, or this is just a drill. Let's say this is just a drill and it's going at a constant speed. Well, before it was going at a constant speed, it was stopped. So in like the second that you hit the trigger, it goes from stopped to a pretty fast speed. And so that that's the obvious acceleration. You know what I mean? If you're on the outside of the drill, you're going from 0 to like now accelerating. And that, so in radians per second, you went from 0 radians per second to, with our drill example, 100 radians per second. So and let's say in pulling that trigger, that took 1 second. So now you have this term, angular acceleration. It's the change in radians per second. You know what I mean? It's the same thing as acceleration is change in velocity, change in time. Angular acceleration is change in omega, change in time. Change in angular acceleration, change in time. And then so for our example, well, that's going to have an angular acceleration of 100 radians per second, or 100 radians per second squared. You know what I mean? All right, so that is very useful, if I can remember why we even did that. Oh yeah, because this is hidden. This is such a hidden acceleration. What the hell are you talking about? We're having a velocity towards the center? That's so not intuitive. Extremely not intuitive. What we need to do as physics students or engineers is just like, hey, if we have circular motion, we just have to know this is the case. You know what I mean? That's why I do this always with a proof, and then go back to the equation, just to make sure I trust the equation. So then when I use this equation, because it's not super obvious if I could even spot an error if I stumbled across an error. How would I double check that? And so yeah, even right here, we know if we grab this string and then we start going around that circle, well, just by definition, we're going to have an acceleration towards the center of the circle. And then in polar coordinates, they just say it's negative omega r. And you could do whatever you want. I mean, you could say this is the positive direction, and this is the negative direction. But in polar coordinates, they're saying, hey, you have an origin, 0, 0, for your angle and then your radius. And then you have a positive. So we have a positive out here. You know, we have 0 angle, but a positive radius. Cool. And so if you're accelerating towards that direction, that's going to be the negative radius. You know, so that's where that acceleration is negative r omega squared. And but yeah, let's see if we can intuit it for our drawing. So we know that we're going to be, and if we accelerate, yeah, this is the bummer about the F equals ma diagram, because oh yeah, this is horrendous, because this is where I get confused. This is why I do these problems, and then I get to here and it's just like, what the hell? I'm observing, let's go back to like my basics. I'm observing acceleration, you know, in a particular direction. Let's say it's cliff jumping. I'm observing an acceleration in that direction. There must be a force associated with that acceleration. Oh, for the love of God, this is so cool. So this is centripetal force. So the only thing that is, so if I'm just, you know, neglect the spring, the string, I'm sorry. That's why free body diagrams are so cool. Sure, we have a string and then we have a mass, but just let's say we don't, and you chop that mass out of outer space, but then you still want that mass to go around that circle. The only way you're going to get that mass to go around that, and the initial velocity tangential is totally irrelevant. Because it's not a form of acceleration in itself. You know what I mean? It wouldn't matter if it's not moving, but we do need some sort of movement. But what we're saying is that the only way for this to go around the circle is to have a force in the direction of the origin of the circle. And that force has to be in that direction. So if we have already labeled it like this, we don't need to put a negative on it. And we know that force, so I mean, just like force of gravity is g(m)(me) radius of the Earth squared, maybe this is where I can really dial in on this acceleration. Not knowing that for radial, not memorizing that acceleration is negative r omega squared, but just, and I like to look at things in their positive or absolute sense, but I want to look at this as, hey, this force, just from the idea that force is equal to mass times acceleration, and from the idea that if this is the only force, if I've just identified only one force, back to our example of free fall, if I've only identified one force, then you must have acceleration. And that's where it was just very fascinating when you get to a problem where you're just like, well, I know that there's a force of gravity, but maybe I don't know of any other forces, but I'm observing zero acceleration. And then the question is why? Well, it's because there's another force. But here, I mean, we've totally taken the tension out of it, and we're just saying I have a mass, and I want to get it to go around this circle. And so now the light bulb goes on that, sure, in this example of like, hey, putting an outward force, forcing it, is the same thing as putting a tension force on the inside. Taking that mass and then pulling it this direction is the same thing as putting an outside force. But for whatever reason, taking this thing, taking it into outer space, and just saying I want to have it travel in a fictitious circle, applying an outside force makes more sense to me. And I know by definition, this outside force, if it's the only force, well, how am I going to say this? I'm just going to go for it. The outside force is equal to the mass times the radius omega squared. The outside force is equal to mass times acceleration. I mean, you have F equals ma, and so every force, well, and maybe this isn't true. Maybe this isn't true. But, I mean, it comes up a few times. That's where it just gets confusing of, like, what side of the equation do you put it on? Because you have force of gravity. Well, that's just mg. So, do I put it on that side? Or do I put it on this side? Well, you put it on this side because all the forces are additive. You might have other forces out there. You know what I mean? And then the acceleration is kind of your net acceleration. So heck yeah. So in this case, I just kind of spelled it out. I said, well, the force has to be that mass times its acceleration. And look at that. The definition of normal acceleration in the radial direction pops out, r omega squared. And for whatever reason, that seemed useful to me. And so let's do it with the string. How would we set up this one? We're going to say F equals ma. This side of the equation, the other thing that we're going to do is this. If you do have the cliff jumper, we have F equals ma. Like, sure, we know that the force side is in textbooks and stuff, but we know the acceleration also comes out of knowing the individual forces, and like the acceleration is gravity. So in this case, but like that's the opposite way that I would do it. So when I with force of gravity, I like the equation. You know what I mean? Because then you get the equation and you can solve for acceleration. So it's just bizarre to me that I can't do the same thing and I'm sure you can with this, but it's just that when it comes to normal acceleration, it's known as r omega squared, and that's the acceleration part. So if we say, here's our force is equal to mass times acceleration. Alright, bummer, my camera cut out, but yeah, we didn't get too far. So yeah, so if we have F equals ma, that we can see that we have a force, tensioning towards the, that direction, and then we have an acceleration that direction, because we have an acceleration towards the center of the circle, and we have a tension towards the center of the circle. And I like to think of things in absolute values, and I was just happy that this works. If you set your origin as the positive direction, sure, this doesn't have to be negative. Like, anytime I see a negative, I just think I'm just going to lose it. But yeah, how would you set this up if this direction is the positive direction? Direction. Well, then your F equals ma would be, well, look at my tension. My tension is negative T. So we have negative T is equal to mass, and then we have negative r omega squared. So that would be, and then obviously the tension is in the negative direction and the acceleration is in the negative direction. And so then you just get tension as mass r omega squared. Okay, sweet. Alright, so I think we need to finish this string problem. And then, yeah, let's just write this down. Tension is equal to mass r omega squared. Because I think this will probably be very similar to the equation that we'll be using for our problem. So yeah, if you have this string just in deep space and it's long as the radius of the Earth, and then you're coming in at that velocity of 464.5 meters per second. And then you grab on. The question is, what's the tension in the cord once you grab on? Okay, so let's do it with our equation. The tension is our mass, 70 kilograms, times the radius of the Earth, 6.73 times 10 to the 6 meters, times r omega. And I don't like the looks of this omega. You know what I mean? I just don't like the number. It just looks like you're never going to remember it, that's for sure. If you're trying to find the, this is in radians per second, angular speed of the Earth, and it looks totally bizarre, you got the right answer. Alright, so we have 70 times alpha r, 70 r omega. So, whoa. I always forget that squared. Holy Toledo. And then square it. And cool, we have a tension of 2.37 newtons. And we already did this one, you know what I mean? Don't you remember? So divide by 4.44, and we get 0.534 pounds. So 0.5 pounds. And so yeah, if you're just floating through deep space and there's a string that's as long as the radius of the Earth, and you hung on to it, you would have to hang on with it would feel like holding on to a pint glass in that direction, you know what I mean? So it'd be pretty easy. It's not like you would be holding it out like this, but you're just holding tension. But it would be 8 ounces of tension, half a pound of tension. And if you wanted to hold on that ride and get back to the same location, you'd hang on for 24 hours. Cool, so that's our Earth. Okay, so now what we need to, I guess the question was how high do you have to be to where you don't weigh anything? And so that requires hey, if this is the Earth, I was thinking the easiest visual way, getting back to the problem, is design a structure that's like a shell or a sphere, you know what I mean, made out of very light stuff. You know what I mean, where you just build up the Earth. So now you have this huge sphere. So now here's the radius of the Earth, and then we're going to say here is radius, I don't know. I'm just going to say R, we'll come up with the letter for it. Radius big. Cool. And now you're out and same thing. Here's North Pole, and then here is the radius big, and we're spinning this direction, omega. And the omega, we're spinning the same speed the Earth is spinning. So if we're out here, holy Toledo, we're spinning hella fast. And just like if we do a top-down perspective, it's a merry-go-round, and we're just farther out. Earth is in here, and even that was pretty, well, it was pretty slow. But now we built a structure that we're way out here, and we're totally getting flung off, you know, centrifugal force-wise. So now what we notice out here is that we do get flung off. So it's identical to, I think, oh, this is cool. It's identical to that scenario where, or maybe it's not. Oh, this is interesting. It's identical but opposite. So now we're going to go to deep space, and now we're going to say, you're flying, man. Like, you are going real fast. But your velocity tangential, it is going to be the angular speed in radians per second of the Earth times this new radius big. Times radius. So in deep space, this is going to be your velocity. And then when you go to hang on to this rope, holy Toledo, it's as heavy as you would weigh on Earth. So the tension is going to equal mass times gravity. You know what I mean? Whatever that would be in newtons or pounds. But that's the scenario that we're coming up with. And so weirdly enough, this shows the this shows the centripetal force. So now we're saying it's just like, if you had this ride, if you come in with this velocity, this mass comes in with this velocity, what force on this mass, even if you have this radius big, to keep you on this ride, and that force is going to be, basically mg. So that's what we're going to find. What we found with our string is it took really hardly any force, because the speed of the Earth is hella slow. Even at this 464 meters per second, that is just very slow compared to how big the Earth is. The Earth just hardly spins at all. All right, hell yeah. So I think I'm kind of on the home stretch here, because like we can we still don't know this radius, so, and then that would be our velocity tangent. But what we're gonna use is probably the equation, and then we're gonna double check it by finding our velocity tangential, and then doing that same thing. Taking a small chunk of change in time of 1 second, and then finding that d, and then knowing that we have a velocity average of that d divided by that 1 second, and then we know that we have a velocity max of just 2 times that velocity average, and that's going to be our change in velocity, and then change in time of 1 second, and that's going to be our acceleration towards the center. And what we're going to find is that acceleration towards the center is going to equal our body weight. Oh, perfect. See, I just came across our first issue with this, is because if we're hella far out, well, it's just like, well, yeah, shouldn't our acceleration be the acceleration due to this swinging thing be 10 or 9.8, because that's how much we weigh out here? Well, yeah, if we weighed that much out here, but we don't weigh that. The only place that we weigh, mg, is on the surface of the Earth, because that's why this equation, you shouldn't get too used to it, because that force of gravity is gravitational constant, mass of us, mass of the Earth raised to the Earth squared. So this is prime place where it's just like I would have made an error making that assumption. So now, you have 2 variables in this equation. So we are saying, so that's where you really do have to go back to the free body diagram. So let's see if we could do that. So we have a free body diagram. Even though we're sideways here, we know there's going to be some sort of force of gravity because this is a mass and then the Earth has a mass. And we're saying this structure, for all intensive purposes, is weightless. The mass of that structure is 0 kilograms. It's just a magical structure. But it just, what this structure does is gives you a visual that you're like, oh, I could visualize that we're just in some like New Zealand bubble, you know, or like the spheres that you get into. Like you throw an Earth in there, and then maybe you're just on the outside of it. You got plastered to the outside, and then you're spinning down the hill. But anyway, so you can imagine this, and then so we're going to have a force of gravity, but that force of gravity is yeah, our mass. Our mass never changes. Cool. And then the mass of the Earth. Because that's the only mass that's why that was the whole caveat of like, sure, this structure is weightless. But then the radius, and this radius is not the radius of the Earth. Don't get that confused. When you do it like this, that's not, you know what I mean. It's the radius between these two. You know what I mean? And their centers too. This is where if you have the center of Jupiter and then the center of the Earth, you gotta measure. You know what I mean? Maybe the actual distances between, the space between the two planets plus the radiuses of both planets. That's going to be this total distance between the centers. Sorry about that. So yeah, that's going to be the force of gravity. All right, hell yeah. So now, I mean, what I do is like, hey, let's do so much, you know, proving simple things to where when you finally do use the equation, you have like a level of confidence. And we have a level of confidence that we even spotted like one error. So yeah, let's go free body diagram, go back to that. And right here is we're going to have that force of gravity. We're going to have a normal force upwards. But our problem, I mean, this is the techie side, is like, hey, I want to be where like I have this normal force, would be a scale also, and this normal force is 0. You know what I mean? So if I'm on the North Pole and I stand on a scale, okay, let's say 165 pounds. But then I go to the equator, same scale, and then stand on that, I'm going to weigh 164.5 pounds because, you know, that centrifugalness, I'm getting flung off. Like, just because it's a fictitious force, don't, like, always have that in your head, that if something is spinning, like, it's trying to spin everything off of it. That is at least one perspective to have, because it helps the intuition. All right, so and so the scale weighed less. So there's two things you can do. One of my problems in one of my videos is like, hey, let's just speed up the spin of the Earth to where we're getting flung off hella, and then this our gravity becomes like 1/6, so we can jump around like the moon. Well, you can speed that up where you're no longer, this scale no longer weighs any force, and then you might actually have to have a string and a rope and hold yourself to the Earth because you're just centrifugally like flying off. You're like, whoa. And cool. So that's where free body diagrams are the place where everything, you know, becomes complex. But we still have F equals ma. This side is the forces, and so now our free body diagram says we have a, you know, we have the force of gravity, and then we have subtracted by a normal force, but we're saying that's 0, and because we're rotating around a sphere, we're not just on the North Pole of this sphere. You know, we're on the side, and we know from, you know, F equals ma. It's this side of the equation that, yeah, that's where I've always put the textbook on this side. Well, yeah, you need to know the textbooks of, you know, circular, that going around a circle causes an acceleration towards the center. You know what I mean? So there is some, you definitely have to have knowledge about what things cause acceleration. All right, so and then, yeah, so that's going to be this side. Because that's the only acceleration that we observe. Because we are going at a constant speed around a circle. We're not increasing our speed. So, yeah, that's the only acceleration in this example. So we have our mass times that acceleration. and that acceleration by definition is omega r squared. And I'm going to keep this in the positive just because I'm going to say, hey, this Fg, that's the positive direction. Normal force is negative, and we have a mass times r omega squared. And I write this wrong all the time, r omega squared. But that's why we have the visual proof in the end, or actually the proving this. Okay, so now we have it. So now we have this side of the equation, gravitational constant, our mass of the Earth divided by, now here you could get into trouble. This is radius big. You know, we've already determined that the big radius, after we made the spherical shell on it, that's our radius big. And that's going to equal mass times the radius omega squared. Cool. Oh, whoa. And this also is radius big. Okay. So, yes. Now we have our full problem. Cool. So we can see that one of these cancel. So we can just, how do we want to do this? Oh, this is bizarre to me. If we, what are we trying to find? We're trying to find the radius of this shell. Like at what height above the Earth. And that's the other thing. Once we get this height, it's not a height above the surface of the Earth. It's the radius from the center. So another place to make errors. You know what I mean? So just know that. Like this radius big is from the center of the Earth to our location. To the center of our body. That doesn't really have a sphere of importance. So there you go. I don't know why I'm wigging out on this. Obviously, if I take this no. Yeah, oh, this is really bizarre. If I take this r up there, it's an r cubed. Oh, so this is fascinating. Whoa, oh, okay, yeah, I never thought of that. So, and then we'll take this m omega downstairs. So we're gonna do two steps at once. So we're gonna go gm mass of the Earth divided by, we're going to take these two things, the mass and omega squared downstairs. Mass omega squared. We're left with this RB, but then we're going to take this upstairs. So now we have the radius big cubed, and we can just do it in one step and go, sorry, I did way too many steps. But there you go. So the radius big is gravitational constant, mass of us, and that's irrelevant, but it's the gravitational constant, mass of the Earth, and omega squared. All right, hell yeah. So, and we're going to have a check on reality. This might not be right at all. You never know. And so gravitational constant, that's 6.67 times 10 to the negative 11. Mass of the Earth is 5.94 times 10 to the 24 kilograms. I don't know. Who cares the units on that as long as you don't mess it up. And then we have omega. Whoa. And that's going to be 7.29 times 10 to the negative 5 radians per second. Oh, we got a square. I'm gonna miss that every time. Holy Toledo. Okay, so I'm going to do 6.67 times 10 to the negative 11, stored as g, so I have this as my gravitation. 5.94 times 10 to the 24. I always store that as alpha e. So we have e, we have g, and this is w already, and now we're just good to go. So we're going to do math cube root alpha g alpha e divided by omega and square it. All right, heck yeah. So now we have a radius of 42,077,956 meters. But now we need to subtract. So it isn't very high. I was surprised. I mean, it's not that high compared to doubling the radius. And again, this question isn't if you're in a spaceship and you go up to this height, what would your weight be? Because no, you're not attached to the sphere. You're not getting flung off a physical thing. You know what I mean? You're not merry-go-rounding this huge sphere that now you're going to be like at the very outside going hella fast. And so that's going to be radius big. I'm going to store that as b, because even right now we can find our tangential velocity, omega b. So we can find the things that we wanted to know. This is going to be 3,685 meters per second times 2.23, let's say. And you're going 6,000 miles per hour divided by like 770. Is that Mach? You know what I mean? You're going 9 Mach. You know what I mean? Mach 9. So I mean, it's but you're just riding an Earth going, you know what I mean, and maybe you're not going to feel that because it's all you feel is just weightlessness, and you're just kind of hanging on to the surface of the Earth. Okay, so this is going to be we got to subtract that 3,370,000. This is the radius of the Earth, because when we do that, this is our height above the Earth. So so we have radius big minus radius of the Earth, and then we get 35, is that million too? If you can't tell on your calculator where it's million or billion, just divide by 10 to the 6, and then just multiply by 10 to the 6, and yes, it's 35. That's a quick tip on me. And then so 957. Cool, so 35 million meters. And I don't know what a million meters. I'm going to divide by 1,609. And so this is 22,192 miles. And I've heard this one in the news a lot. But yeah, haven't you ever heard of 22,000 miles? That's where... and so this gets us closer to the space elevator effect. You know what I mean? If we have a structure... any weight above that 2,192 miles height above the surface of the Earth, you know, because let's figure out so the radius of the Earth divided by 1,609. Well, there's 4,000 miles of radius of the Earth. You know what I mean? It's potatoes compared to 22,000, but you can see that you could make critical errors by mistaking the height above the Earth, you know, for this rate. If you said the radius big was the height above, that would be RB divided by 1609. You would be mistakenly, that's an easy mistake you could make. Because you could be saying, hey, I think the height is 26,000 miles above the Earth. Alright, hell yeah. But all this problem was for me was to get like that aha. And it just clicked even just right now, that aha of like, oh, I get it. Because even this equation's not a function of mass. You get any material of mass out to that location and spin it in line with the Earth, you know what I mean? Because that's what the space elevator is going to be. It's identical to having a structure all over the Earth and having thousands of elevators, you know what I mean? Just making a structure. So, I mean, the space elevator will be the first thing that could be physically possible. The second thing that would be fascinating would be like making a structural shell out to here. Obviously, that's going to be hella heavy, but then you make it even crazy bigger, and then every part of mass outside of this zone, you know what I mean? You would make the structure just to get real heavy mass out here. Then if you did that in a sphere, this mass would hold tension on the other mass and make it weightless. So that's fascinating. Where it's but even that I don't, and I like this. I like the idea of physics where it's just like I think people struggle, even students, they struggle with learning physics fast because they hit these roadblocks of like I'm skeptical. I don't believe you until I run the equations for myself. I'm not just going to believe something. And it happens just even in dinner conversations. People will think the actual opposite of what actually happens, just because that's where their intuition thinks things are going. That really dampers your learning because you're learning stuff wrong. But the other aspect is to not even make the attempt of being wrong. You know what I mean? Make the attempt of being wrong and then you know, keep at it and then get the right answer. A lot of my work, anytime that you see me kind of struggling with the concept, Well, sure. Maybe listen in because I'm coming up with those anecdotes that are very useful. But obviously, it's something that I haven't got 100% dialed. But we're working towards that. Heck yeah. That understanding. So right now, yeah, I kind of have an understanding that, yeah, stuff or a matter that's that far away that's still spinning with the Earth like it was in a straight line. That's why you can have a space elevator, and the second the Earth rotates once, it's still in the same location. And it makes sense. It's like, hey, could you have a space elevator connected to the North Pole? Like, that would be the hugest critical error from like a physics perspective. You're just like, well, that was dumb. And no, it has to be attached to the equator. Like, at least from this problem, you can gain that to be like, if you attached, you're like, okay, we're ready to attach the space elevator. Okay, let go, and then it would just all crumble and fall to the North Pole because you don't have at least centrifugal forces. So, and the space elevator is like an embodiment of centrifugal forces. But there was a couple aspects in here where we realized, oh yeah. To have that mass ride that circle, you have to put a force on it, whether you push it from the outside or you tug it from the inside, and that is centripetal force, centripetal. Cool. Alright, so we're going to do one more thing with this video, and we're going to prove that radius big produces a velocity tangential of 3,068 meters per second. We're going to take 1 second increment, and let's hold up. What were we trying to find? Because the acceleration is what we were trying to find. And the acceleration, we were saying, doesn't have to be gravity. So that's the wild thing. So right now, let's do two things. Let's know that this acceleration has to be less than gravity, but let's get a check on reality of that. So now we're going to say this is our height above the Earth. Well, no, we just have radius big. So radius big is our radius from the center of the Earth. Cool, and we have this force of gravity. So we know force of gravity, and we have F equals ma. And let's say the structure doesn't exist, and we just... So let's say this structure does exist, and you're on top of it. So now you got that like, oh, wow, that's amazing. And then on that structure, hey, you have a little swimming pool, and you have a cliff. Same thing. We're going to jump off that cliff now. We have a mass, and we know from our textbooks that we have a force of gravity between the Earth plus that structure. The structure is massless, but you have the mass of the Earth. And just a huge distance, and this is radius big. But at least you know that. So we set up our free body diagram, chop that thing out outer space, and say, hey, we are going to have a mass times acceleration, and F equals ma, and we will have this check mark on acceleration. We just don't know what it is. So we need to identify the forces that could be on that mass. Well, we know that there's a force of gravity. Hey, there's just air underneath. There's no other forces. Cool. So now we throw this into this side of the equation, and we get force of gravity is mass times acceleration. And let's do it this way. Let's solve for acceleration, and that's going to be force of gravity divided by mass. And now let's throw in the equation for gravity. That's gravitational constant, our mass, mass of the Earth, and then divided by, hey, let's keep it. We're just focusing on the force of gravity right now. So GMME divided by radius big. That's the only thing about this force of gravity equation when you're using it for other celestial bodies or things outside the radius of the Earth is that you have to vary that. This is going to change. Your radius between what you're trying to, the mass that you're trying to analyze and the other big mass, the center of it. So this is radius big squared, and then we're dividing by mass. So cool, mass cancels, and now we have acceleration, which is gravitational constant, mass of the Earth, divided by radius of the Earth big squared. And we get an acceleration of 0.22377 meters per second squared. And this is blowing my mind because it's just like, whoa, you don't need to... you don't need the acceleration due to something spinning doesn't have to be crazy to make us go weightless, because once we're that far away, we're already, our force of gravity is so low. So that's the other thing. Like, how much do I weigh in newtons, the force of gravity at radius big? Okay, so now we can just do it on a roll. You know, I mean, we got alpha g. Our mass is 70 times 70 alpha e divided by radius big squared. And so we get, we're 15.66 newtons. That's it, divided by 4.44. So even out there, we're already 3.42 newtons. If we stood on a scale out here, and this is fascinating to me, because what this says is like the Earth spins slow. Like, even if you're out here, the Earth is spinning slow. The acceleration due to the Earth is spinning is snail pace. It's so little, even if you're far out here. But if you're far out here, you're just farther away from the Earth and you weigh less. So that is fascinating. You have two things that are balancing out. And again, you could be at the North Pole, and sure, you still just weigh 3.5 pounds. But if you let go of that weight, you will fall to Earth. Compared to, because on top of that sphere, you're not spinning. You know, you're not going around, you know, like that. But if you're out here, and you keep up that velocity, you will. That's what staying in orbit is. You know what I mean? Just because that's why I did this visual sphere. Because then you can just get rid of the sphere. You can set something at that, you know, height, 22,000 miles, and put with it 3,068 meters per second times 2 is like, yeah, 7,000 miles per hour or something, and 8,000 miles per hour, Mach 8 or whatever we came up with. And so that would be a satellite in orbit at that height. All right, hell yeah. Okay, so I think that does it. And now we're going to do one more thing and just prove. Let's see if we can do it now. So here's radius big. We're going to come in here like that. Okay, here's our tangential velocity, velocity tangential. That's it's omega times radius big. It's radians per second, something, you know, radians times something normal. Radians times radius is something normal. I guess that's the equation that I use. Here's my distance d. Here's my radius big. This is going to be radius big minus radius big cosine of my angle. The angle is that. I'm going to do a change in time of 1 second. We know that omega is radians per second. And so my change in radians in 1 second is just going to be omega. So my angle is going to be omega times 1 second, to make the units make sense to you. And then distance right here. Oh, see, I already messed this up. You know what I mean? So this is distance. It's the total radius minus the radius cosine angle. You know what I mean? That's d. This distance is just RB minus d. I think that's the, you know, the total radius minus that little d. That's the easier thing. Or this distance right here is RB cosine theta. So a couple ways to write it. All right, hell yeah, home stretch. And yeah, we have zero velocity towards the radius, and our velocity. Let's get our velocity. That's omega times radius big. Yep, that's that. And I'm going to store that as alpha u because I don't know if alpha v in my calculator is already taken. How do we do this? Oh yeah, we need to find this distance. I think that's all. I don't even think tangential velocity comes into it, does it? Not really. So we need to find that distance. It's going to be radius big minus radius big cosine of our angle. Our angle's in radians, and that's omega. And now we just need to be in radians. We are. So this is our angle. Oh, dang. And we spin quite a bit. Is that true? I feel like that can't even be true. Alpha B is still really big. Yeah, we're still spinning an omega. Let's back this truck up. Or why is this? Because I said if this was just the radius of the Earth, and we have the same omega, and omega hasn't changed, and then I do a change in time of 1 second, then I'm going to have angle of omega, and then I'm going to go cosine of omega. I guess this D is substantial. Oh yeah, duh. Because if the we have something like this, and then we have a huge sphere. So sure, and then I don't know what I was thinking, but yeah. So this distance is going to be a lot smaller. I was thinking I was coming up with the angle. So I apologize. So yeah, so we have radius big minus r cosine of the angle. And yeah, we move this distance, so we actually have a bigger velocity. Oh, duh, yeah, so our velocity towards the center is going to be bigger. So our average velocity towards the center is that distance times the time. And we go for 1 second, so it's basically just that distance. Our max velocity to do things fast is obviously just double that, because we have 0 velocity towards the radius here, and at this time we must have to have twice the average to have an average velocity of that, so towards the radius. So times 2, so we have a velocity max of 0.22377 meters per second. Definition of acceleration is change in velocity, change in time. And so that's going to be our change in velocity, because we went from 0 to that. We did it in 1 second. So this is our acceleration, 0.22377 meters per second squared. Now, it's approximate, you know what I mean? Just like using integration, you take this slice, change in t just to like a thousandth of a second. You do that, you're going to get a much accurate, because your velocity towards the radius will be, you know what I mean? Like, that's what I said, is like, if you're out here, you know what I mean? Like okay, you should have been here and you're here. So, like, it looks like you went that way, but with your change in velocity. Alright, hell yeah. So home stretch, my camera overheated, but yeah, if you do too big of a sweep of a change in time, it doesn't look like you're actually traveling towards the radius. But if you really break this down really tiny in this distance, heck yeah, this distance is basically in the same direction as the radius. So that's the difference in these numbers. But I think, heck yeah, they're basically the same. This number just, yeah, it's the same to 5 decimal places. So that was pretty cool. So even just taking 1 second, you get up to 5 decimal places of accuracy. Okay, I think I'm going to end it, for my understanding, even if we have the Earth here, at any radius, my question is, like, and if because it's the space elevator thing, if I'm traveling at the same speed as the Earth, is in a plane like that, the question is, like, and I'm standing on a platform, the question is, like, what is my weight? And that's kind of like you have to do this and throw a scale underneath your feet. And then have that, because the scale is going to generate weight. So let's do the free body diagram. So we're going to have a normal force, and then we're going to have a force of gravity. And then we're going to have, and is this the way to do it? Can you also, on this diagram, maybe in a dashed line, put acceleration? You know what I mean? So then when you go to your F equals ma, we're going to sum the forces. And in this time, I'm going to say this acceleration is negative r omega squared, like the textbooks. So that must mean that this is the negative direction and this is the positive direction. So now if I say my forces, sum them, normal force is in the positive direction, and I'm going to say minus the force of gravity, which is gravitational constant mass of the Earth, divided by this radius. I'm just going to say radius x, so you know that it's not the radius of the Earth. Okay, and then that's going to equal negative Rx omega squared. Now, I just want to make sure that made sense. You know what I mean? I just, too many negatives. It's just like, what? Well, and the one thing that trips me up is like, well, are we, like, we're saying, because sometimes you have like this, you know, even the cliff, you're like, okay, this is mg. But what if you're saying the gravity is negative 10 meters per second squared? Now, what is this referring to? Well, it's referring to the fact that this is your positive. All right, so it's referring to hey, this is the positive direction. So yes, your speed is increasing in the negative direction. You know what I mean? So you're gonna have a higher negative speed, and because this is the direction of your negative speed. So I don't know. Yeah. Negatives trip me up though so much. And in free body diagrams, you have to have kind of a handle. That's why you want an intuitive sense of what's happening. And then because there's just so many places to throw in an extra negative or not have a negative. And I'm just going to make sure that this one jives. Because we have, on this side, we're going to have negative radius big omega squared. And then we're going to add it to, when we take this to over here, we're going to add it to alpha g, our mass. Oh, and we're totally forgetting things. We have to add our mass. So F equals ma. Our mass is over here too. So we have our mass times that acceleration. That's the acceleration term in the normal direction. Yeah, because I was just like, yeah, because masses have to cancel on both sides. And I'm going to say 70 stored is alpha m. So, or what is alpha m? Yeah, 70 stored as alpha m is our mass. All right, sorry about that. Yeah, so let's now redo this one. This is mass, alpha m, alpha m, parentheses, negative alpha r, alpha omega squared. So that's that term. And then we're going to, this is negative over here, so we're going to add it to the other side, right? So we're going to go alpha g, alpha m for our mass of the Earth is alpha e, divided by, and for these alpha, holy Toledo, yeah, I'm confusing this, you know what I mean? For our problem that we did, this is for any radius, but we want to double check our problem. So it's g, m, mass of the Earth, divided by radius big squared, is equal to mass minus radius big omega squared. You know what I mean? Just because we're trying to figure out that, isn't that normal force 0? I mean, that's our check on reality, if you're seeing where we're going with this. So yeah, so this alpha b. So there we go. Mass minus radius big, which is alpha b in my calculator, omega squared. Plus this side, gravitational constant, our mass of 70 times the radius of the Earth is 6 times, basically 10 to the 24 kilograms, and then divide it by radius big, alpha b squared. Hell yeah, we get 0, and that's a great place to end, you know what I mean? The free body diagrams, these are the things that trip me up the most, and so I want an intuitive explanation of what's happening, because I get the free body diagrams, but no one does. I mean, because you have a free body diagram, and then you're just like, well, do I put stuff over here or over here? And in this case, it's such a cool problem, because, hey, you are throwing a value in for acceleration. That's what you're observing. And we do have a representation of what that acceleration is. We have an equation that says if that's the only thing that's causing acceleration is towards the radius, hell yeah, that's going to be the acceleration. Cool. And these accelerations are additive. If you had that acceleration plus another acceleration in the normal force, in the normal direction, those two are going to add together, and the additive or subtractive nature of that is going to change that normal force. You know what I mean? So, okay, hell yeah. But just to check on reality, that's a great place to stop. Thanks for joining me, and that's a video.